So hello everyone, my name is Mihar Channa and today I am going to present on the topic oxygen analyzers. Oxygen analyzers operate by detecting and measuring the concentration of oxygen in gas sample through its distinct physical or chemical properties such as electrochemical reactions, paramagnetic effects, thermal conductivity or light absorption and converting these signals into precise oxygen level readings. So now moving on to the introduction of oxygen analyzers. Oxygen analyzers are critical instruments used to measure oxygen concentration in various gases. They play a key role in process control, safety, and quality assurance across diverse industries. So why it is important? It is essential for process control, safety, environmental monitoring, and medical applications. Now moving on to the applications of oxygen analyzers. The first one being the industrial applications, for example combustion control, gas purity, etc. The second one being the medical applications, for example respiratory monitoring. And the third one being the environmental applications, for example air quality assessment. So now moving on to the types of oxygen analyzers. There are primarily four types of oxygen analyzers. They are paramagnetic analyzers, which utilizes the magnetic properties of oxygen for measurement. It is suitable for high purity oxygen analysis. The second one being the electrochemical analyzers, which uses an electrochemical cell, galvanic or fuel cell to detect oxygen levels. It is common in portable and medical devices. The third one being the zirconia analyzers, which uses a zirconium oxide sensor operating at high temperatures. It is ideal for combustion control and flue gas monitoring. The fourth one being the infrared analyzers, which measures the absorption of infrared light by oxygen molecules. It is mainly used for gas mixtures with low oxygen levels. Now moving on to the paramagnetic analyzers. It is based on the principle that oxygen's paramagnetic property makes it strongly attracted to a magnetic field. In the analyzer, oxygen is pulled towards the magnetic field, causing deflection or pressure changes. The sensors detect this movement, generating a signal proportional to the oxygen concentration. The signal is then converted into a precise oxygen level measurement. The key components of this type of analyzers are number one being the magnetic field, which creates an area where oxygen molecules are attracted. The second one being the measuring cell, which contains the gas sample and reference gas, which detects the magnetic effect. The third one being the detector, which measures the magnetic force acting on the gas. So the advantages of using this type of analyzers are that it is highly sensitive and produces very accurate results. It is a very fast response time and that it is non-depleting in nature. So the applications of this type of analyzers are number one being the industrial gas analysis, second one being the environmental monitoring, and the third one being medical respiratory systems. So the limitations of using this type of analyzers are that it is highly sensitive to temperature and pressure changes and that it is not suitable for environments with corrosive gases. So now moving on to the zirconia analyzers, it is based on the principle that it utilizes a heated zirconium dioxide sensor as a solid electrolyte. At high temperature of about 600 to 1000 degrees Celsius, zirconium dioxide becomes an oxygen ion conductor. Oxygen ions migrate across the sensor, creating a voltage difference based on partial pressure of oxygen in the sample gas. The generated voltage EMF is used to determine the oxygen concentration accurately. So the key components of this type of analyzers are number one being the zirconia cell, which acts as a solid electrolyte. The second one being the heater, which maintains a high operating temperature of about 600 to 800 degrees Celsius. And the third one being the electrodes, which measures the generated voltage. So the advantages of using this type of analyzers are that it produces highly accurate results and it's stable. it is effective in high temperature and harsh industrial environments, and it has a long operational life with proper maintenance. So the applications of this type of analyzers are combustion control in furnaces and boilers, oxygen monitoring in process industries, and automotive exhaust gas analysis. So the limitations of using this type of analyzers are high power consumption due to heating requirements, prone to sensor drift over time, and that it is not ideal for low temperature or moisture rich environments. So now moving on to the electrochemical analyzers, it is based on the principle that it utilizes redox reaction at electrodes. The oxygen reacts at the sensor, generating an electrical current proportional to its concentration. The key components of this type of analyzers are number one being the electrodes, which are cathode and anode. The cathode is made up of noble metal. The second one being the electrolyte solution, which is primarily a potassium hydroxide solution, and a membrane which allows oxygen diffusion. So the advantages of using this type of analyzers are that it is portable, cost effective and easy to use, and that it has good sensitivity for low oxygen levels. So now moving on to the case study where we do oxygen analysis in combustion control. The objective of this case study is to achieve the optimal air to fuel ratio in industrial boilers for efficient combustion. The implemented solution was to implement zirconia oxygen analyzers for precise monitoring of oxygen levels in the flue gas, and the real-time oxygen data provides feedback to the control system. Adjustments were made automatically to combustion parameters. The outcome of this solution was that it significantly improved the fuel efficiency and reduction in harmful emissions such as carbon dioxide and various nitrogen oxides. It lowered the operational cost. So now moving on to the future trends in oxygen analysis. Number one being advancement in sensor materials. So incorporation of advanced ceramics and nanomaterials have greatly improved sensitivity and durability and has enhanced resistance to harsh industrial environments. The second one being the integration with IoT. Now the emergence of smart oxygen sensors for real-time remote monitoring. The second one being integration with IoT. The emergence of smart oxygen sensors have made real-time remote monitoring possible and enables predictive maintenance using AI and data analytics. So now we can conclude that oxygen analyzers play a vital role in ensuring quality control, safety, and process efficiency across various industries. They are integral in applications ranging from combustion control and medical diagnostics to environmental monitoring. The key takeaways are to choose the right type of oxygen analyzers is critical and should be based on specific application requirements, including accuracy, operating environment, and cost considerations. So, thank you everyone. That was it from my side.